After the first decade of the very success of remote sensing, then the community started to realize that there is no trustworthy measurement without uncertainty. But uncertainty is something that was never much loved by the remote sensing scientists, partially because of the complexity in measurements in the research areas. Since the 90s, there has been much effort in marrying remote sensing with metrology. Not meteorology, but metrology, the measurement science, the science of measurements. But so those first effort was not so general, and they were quite isolated until around 10 years ago, when a satellite sensor became too complicated that it was hard to validate satellite measurements to evaluate the uncertainties of the satellite measurements. So the in situ measurement became needed. Those in situ measurements used for validating the satellite measurements, we call them reference measurements. Those reference measurements are also used for vicarious calibrations of the satellite sensors. But for doing that, those reference measurements have to have certain quality, and these requirement produced the term fiducial reference measurement, FRM, around 10 years ago during the Sentinel-3 validation team meeting. So FRM is defined very clearly in this recent article, and I really suggest to people who deal with remote sensing to check this article and to understand the basic of FRM, because it is possible that in the near future it is impossible to publish any articles or publish the result without evaluating the uncertainties of your measurements, or without handling the uncertainty in some way at least. The FRM sets up a general requirement for the measurement protocol, instruments, data handling, and dissemination as listed, as simplified on this list. So basically, first of all, the instruments have to be calibrated, characterized, and traceable to the standards, preferably the SI unit. Second, the measurement protocol have to be set up and agreed within the community. Then the protocol have to be followed by the community and during the measurements, and uncertainty have to be evaluated. Fourth, the intercomparison between measurements have to be carried out, and then everything you do or you don't do, you have to document them, and the documentation has to be available for the other to evaluate. This article I already showed on the previous slide, so it also proposed the maturity metrics, so that the interested work group or lab can check the maturity metrics and can place themselves on the FRM maturity level. There are a lot of big projects going on related to the uncertainty in the remote sensing. As you see, ESA alone already has initiated at least 10 projects with the FRM in the project's names. And from the list, this is not exhaustive, but from the list you can see that those FRM projects are belonging to many different types of sensor, satellite sensor, and many research areas in remote sensing. Some of them can be important for the work groups in Tartu Observatory. Right now, Tartu Observatory is leading the FRM for SOC, which is dealing with uncertainty in ocean color remote sensing. The first FRM for SOC already started and ended. The second one is going on and probably ending next spring. So the following examples I take from the above water measurements, measurements, but the requirement for the instrument characterization and calibration must also apply equally in the same way to land remote sensing and atmospheric remote sensing. So in ocean colored measured by satellite and by the in situ sensors, the typical output quantity is reflectance, remote sensing reflectance RRS. We typically use a setup of 3 sensors, like in the picture. One measures upwelling radiance, one measures downwelling irradiance, and one measures downwelling irradiance. And from those 3 quantities, you can use the formula here to calculate the remote sensing reflectance. And of course, from this formula, you can also derive the formula for the uncertainties of remote sensing reflectance. With this, I want to summarize some of the very important findings of the from SOC1 project. In SOC1, tens of in situ sensors were participating in first of all in the lab comparison and then outdoor in field comparison on the Lake Garrigu. This graph on the left shows that the expanded uncertainty of the remote sensing reflectance in 2 cases. The first case is when you just graphed any calibration coefficient you happen to have for your instrument, and the second line is the second case is when you use a fresh calibration coefficient provided then by observatory's lab. And then you can see from this graph, you can see that basically if you the expanded uncertainty of case 1 is very high. Basically, that means that if you just use any calibration coefficient you happen to have without regularly calibrating your sensor, then the measurement becomes essentially pointless because the uncertainty is too high. But as soon as you regularly calibrate your sensor, then you can immediately reduce the expanded uncertainty to some tens of percent. This graph shows the agreement between the freshly calibrated radiometers in the lab, in the field conditions and in the lab condition. So in the lab conditions, you see here the instruments agree very well to each other. But as soon as you take those instruments to the field and to measure in the typical field condition, measure the same object and in the same way side by side, and their agreement is around 5-6 times worse. This happens because each radiometer has their individual characteristics, and those characteristics react differently to the conditions on the field. Those conditions, the spatial distribution, spectral distribution, the temperature, ambient, and they are different from the lab setup. So with this second graph, the conclusion is that calibration is very good, but again, calibration alone is not enough to ensure the quality of the measurement, but the instrument has to be individually characterized as well to achieve low uncertainty. So this is the findings, some important findings of the first FRM for SOC project. The second FRM for SOC project is dealing with characterizing each radiometer, and the analyzing is still going on. Here I present our current understanding of the different component, how different properties of one given radiometer impact is the uncertainty bucket. And as you see, there are many parameters that influence the uncertainties, and practically it is possible to find corrections for many of them, but the correction can be complicated, and after so many corrections, we are not sure anymore, not as confident anymore if where we are and if we are doing everything right, if the result after those many corrections is still valid or not. That's why the team in Tartu Observatory concluded that we need a reference radiometer to that reference radiometer should be performing better than other instruments and can be used directly on the field during intercomparison as a standard. So that reference can help us to validate if our characterization and correction are still okay. And that conclusion became my PhD project that started this academic year. Basically, for this project, the tasks are very ambitious. First of all, I have to design and build that reference instrument. Second, I have to characterize the instrument and build a comprehensive uncertainty budget for it. And then third, I try to test the instrument in a field campaign. We are in the designing process, and right now I'm intensively collecting the information on the instruments with similar functionality. And this is very raw, very preliminary concept in our heads, how the reference instrument would be. Again, this is very raw idea right now, but we present here the main components that the reference should have. For example, the reference instrument should be thermally stabilized. And then some similar instrument they have the box, the thermal control box, this orange box. And for other similar instruments, for example, Kasume, the box is filled with nitrogen to protect the optical components from humidity and oxidation. And our reference instrument will measure both radiance and irradiance quantities, so it will have two input optics. And measuring upwelling and downwelling radiance means that whether the radiant input will be rotated or the full box will be rotated. We'll see. The detector probably will be separately cooled. And yeah, we use double monochromator instead of the array spectrometer just to. Yeah, this is what we try to test right now. And yeah, this is ambitious and big project, but we will do the best. That's all. Thank you for your attention.